Please welcome Kevin Coggins, Vice President and Positioning, Navigation, and Timing Lead at Booz Allen Hamilton.
Hey, good morning, everyone. Quite an honor to be here with three of my close friends that work position, nav, and timing across the industry. I've got Mr. Drew Morin. Drew leads federal cyber security at T-Mobile. I've got Dr. Brian Teeple from OSD. He's the Deputy Chief Information Officer for C4, and he's an aerospace engineering PhD graduate from MIT. And finally, I've got Dr. Greg Goot, the Chief Technology Officer from Satelles, the first provider of low Earth orbit PNT technology. Greg is a graduate from Stanford University, PhD in electrical engineering. So quite a diverse cast here, and we're going to talk about what is this PNT thing, and what is our dependence on it? Why does it even matter? So one thing to note, the loss of PNT, we'll start there, would cost the US in excess of $10 billion a day. It's a huge impact. So you can imagine the worldwide impact is pretty enormous. There are very few technologies we have that don't have a dependence on positioning, navigation, or timing information. Most of the US critical infrastructure is critically dependent on PNT. That's power generation, telecommunications. That's your ability to transport goods and food. So a lot of our system is very dependent. We're going to dig into that today. Most of you know GPS, right? The global positioning system. That's the main way that we get PNT information today. That's an old technology, but it's in everything. And when you have old technologies that are in everything, you have vulnerabilities. You know, GPS receivers are like computers, except we don't patch the software in a GPS receiver. We don't upgrade these GPS computers like we've learned to do with the computers that we use every day. So we're going to talk about what that means, what the impacts are of that. So the first question I have for the panel, you know, I'd like to talk about first, from your perspective, your views on our dependence on PNT, and what you see as some of the biggest challenges you face in what you do. And we'll start with Dr. Teeple.
Okay, thanks. Just to give people an idea of what I do in my office to kind of frame this question, we have oversight of the GPS system. We also have oversight on the US Naval Observatory, which is responsible for producing the time, goes to GPS that, you know, kind of synchronizes everything in the world. So we're also looking at the user equipment and how it's used across the entire department. So it's one of those things that was originally developed for the military. People think of it as providing that military advantage, especially over a lot of our opponents, being able to give precise guidance to munitions. But what they don't realize is it's also crept into everything that we do, from logistics. The timing is essential to communications, being able to encrypt the signal. So if we were to lose the GPS signal, one of the problems that we have is we become so dependent on it, we're not used to fighting without it. So that if it goes out, we don't necessarily have all those things in place, and we're in that process of bringing those back, in addition to having, you know, backups, but also being able to fall back to a more graceful period of where we can still get the job done, maybe not as efficiently, maybe not with quite the effects, but we're not at a complete standstill.
Okay, thanks, Brian. This sounds pretty serious. And Greg, I know that your company is looking at how to help provide more resilience and more PNT capability. So what are some of the challenges you see we face, and how are you addressing them?
Yeah, you know, when I think about this problem as a whole, or this opportunity as a whole, I think of in the early 1980s, the United States had generally considered what was generally considered the most advanced communication system in the world, led by the Bell system and AT&T. And so I think there's an analogy here where GPS is broadly considered the most sophisticated PNT system in the world. But with the breakup of AT&T, it created this ecosystem that we have today that you can hardly even see the original roots in there. I mean, what it is to make a phone call. My daughter doesn't even know what a phone call really is. She just texts. So I believe we're on the verge of that with PNT. with all kinds of new technologies, and of course I represent one of those technologies, which is to provide that capability from low Earth orbit satellites. And I think the greatest challenge is part of its policy. So the breakup of AT&T would have never happened if there wasn't a forcing function that allowed that to happen. And part of it is awareness. Most people just don't realize that there are 4 billion GPS devices in the world and that our economy depends on it.
So you raised some great points there, and you kind of helped me segue to the telecommunications side. And so, Drew, my question for you is along the same lines, except I'd really like to understand, when we do send a text, what really happens? What is that dependence on time, and how does T-Mobile look at time and positioning with the infrastructure that you provide?
Okay. So thank you for having me here, by the way. I'm with this distinguished panel. I feel like I'm cutting it short by not having a PhD, so I apologize for that. I'll work on that. Okay. From T-Mobile perspective, we look at position, navigation, and timing. We're in the communications business. Okay, we're here about providing our customers with reliable connectivity, communications that they can depend on when they need it most. Okay? So when you look at position, navigation, and timing, you start off from the standpoint of position, knowing where you are in a network. For example, for a 911 call, the first routing of that call is based on where you are in the network, not necessarily a GPS fix. Right. People may not realize that. So the general position in the network, maybe cell tower base, cell sector, is used for that type of capability. So position is always an important thing. And there are other use cases for position as well. We're talking about validating where you are when you're using an ATM or something of that nature. When we look at navigation, most people are used to navigation. They understand that the signal can be used to help get them from point A to point B, and they rely on that. But to the carriers and the telecommunications infrastructure, the most important one is timing. Because without timing, we can't ensure that the data gets from the wireless device to the tower. They have to synchronize with each other. When you send a text message, you're sending a whole series of different datagrams, if you will, or messages to send that one piece of text. You're sending out control information to say, I need to go and send this text from point A to point B. The network itself has to recognize the beginning of this data stream. It has to be there right up front so that when the rising edge of the data comes in, it's not dropping bits. Because if you drop bits, you get jitter, you get snow on the video, or in the case of a text, you might get a failure because some of the data is missing. So we have to deal with both the leading edge, the framing of it, as well as understanding the frequency. Because when you think about communications, if I'm speaking right now, you look, you see my mouth move, so you know I'm going to say something. Hopefully that means you pay attention. That's kind of like the frame, leading edge. I'm also making a whole bunch of noises and sounds. These are frequencies. And so if we don't have the frequencies set that we're kind of aligned with it, you're not going to understand what I'm communicating as being words. So from a telecommunications provider, we need to not only be able to frame when the data is coming in, we also need to be able to ensure that the frequencies are recognized between the sender and the receiver. So timing is very critical to all of those capabilities.
So it sounds like your system wouldn't work if you didn't have
no, it wouldn't work if we had no timing. That's correct.
And Brian, you mentioned the U.S. Naval Observatory, and you mentioned the source of time, right, for everyone.
Yes.
For Satellus capability, for GPS, for cell phones, for all these users of time. Where does USNO get time from?
So they have multiple atomic clocks in basically 2 locations. One's right here in D.C. down near Foggy Bottom, across from the Vice President's house at the U.S. Naval Observatory. They also have them out in Colorado, and they take averages of the times to get the most precise. They're also responsible for measuring how the Earth's moving. So when you get your position, if you want to see where you're actually in the map, you need to know where the Earth is at that time.
Right.
And they produce all that information that goes into these devices that help you, figure out where exactly you are on the map. And, in addition to knowing exactly what is the time, so when, I say the signal starts here, he knows he's on the same time reference and knows when it should arrive.
Sounds extremely complicated. I think we'll all have PhDs by the time this panel's done. So, this is very, I've worked this space with you gentlemen for a number of years, and it can be very complex, right? There are some simple ways to look at it, though, right? We've got this foundation of time. We have to distribute that time information out. and we have to calculate position information based on other variables and time. Easy to say, very difficult to do. One of the most challenging programs I've seen is the GPS program in DoD. We spend hundreds of millions of dollars a year on these GPS programs just in DoD, much less what we spend on the commercial market, which is hundreds of millions of more dollars, right, in revenue a year around these P&T devices. And we've woven it into everything. As simple as it can sound, and then as complex as it really is, it can be easy to break. It can be easy to disrupt. So what I'd like to talk about quickly are what are some of the challenges you see, some of the vulnerabilities in the current technology we use, and what do we need to do about it? And Brian, we can start with you.
So that's one of the things we pay high attention to, because whenever we go into combat, the enemy is looking at how can they get to disrupt it. You know, if you can make the bombs not have that precision, go off target. So some of the basic things they look at: can they jam the signal? So you're no longer receiving that signal. You know, you're only as good as the last time you got the signal, knowing where it is. More sophisticated, people use the term spoofing, but that's where they generate a false signal and make you think you're somewhere you're not, which in some ways is even worse than not knowing where you're at. You know, if you think that's the target, you think you should blow it up, and that turns out to be something, your own forces, a civilian site, that way is much worse. And then, as you mentioned, cyber, especially as this becomes networked together, there's many ways to attack that. The receivers, either disabling them, causing them to think, once again, that you're somewhere different, or it's a different time, which can result in all kinds of different things. So we're looking at how do we counter each of those, and it kind of depends on where you're at and what you're doing. For an important nuclear site here, we may not be worried so much about jamming, but we're more worried about the cyber attack. If we're on the front, that's where they have the jammers, that's where they're going to be able to attack it. And these are things that move not just from nation states that we may be fighting, but they're things that smugglers, terrorists, can get their hands on. So it's becoming more important as we look in defending the homeland.
And Brian, just to clarify, you're kind of speaking from the perspective of GPS jamming and GPS spoofing, right? And just so everyone knows, the global positioning system is a pretty low power signal by the time it gets down to the Earth from the satellites, because as the signal travels through the air, it continues to get smaller and smaller and smaller because it runs into things and degrades. And it's only transmitted on 2 frequencies. And so if I'm a bad guy, and I know it's low power, and I know where the frequencies are, I know where to attack. And it's not a lot for me on the ground to send out a low power jammer and still be able to overwhelm it. And so those are some of the challenges we face with protecting GPS. And the problem we have is it's so hard to change from GPS to other things, right? Because we put it in so much. And so where I want to segue this question now is, given what I just said, what do we do about this? What are some of the options we have, and in addressing this problem? And Greg, I'll go ahead and jump to you.
Great. So one way to think about time is that if you push it through a wire, let's say the internet seems like a great way to distribute time. It turns out that when you send the timing signal out, it goes through all these routers and so on, and it goes through a complicated network. And by the time you get it, it's actually very distorted. So I think to set the stage here, we're not talking about seconds and minutes here. We're talking about billionths of a second. So for example, the power grid. If 2 transmission stations are generating power and the signals don't line up, and you're talking about millions of watts of energy, and those signals don't align, things can go terribly wrong. So the beauty of satellites is that when you send out that pulse, it literally is like light. It's just at a different frequency. And it travels in a straight line, and there's no routers in the way, and so on. And that's really at the heart of the genesis of our company, was realizing satellites are great. how can we do this differently? How can we do it better? And it turns out that there are different kinds of satellites. So the original GPS satellites are mid-Earth orbit satellites. And as you said, because they have a reasonably high orbit, they take energy from the sun and they radiate it all over the Earth. And by the time it gets to you, it's a very quiet signal. It turns out that low Earth orbit satellites are much, much closer to the Earth. They're about 25 times closer. And what that means is that the signals that we deliver is 1,000 times stronger. And that means it can penetrate buildings, and it also means that it's much more difficult for a bad guy to jam or spoof the signal, because instead of using, let's say, a very small device that's a few watts to overwhelm a GPS signal, now you need a big thing that uses a lot more energy and so on to overwhelm what we call satellite time and location. That's our service, STL, provided by Satellus. Now, there's other ways to skin the cat, and I think there's going to be an ecosystem of solutions. But the idea of using low Earth orbit satellites to generate a much stronger signal, I think its time has come. And we're delivering our capability all over the world. And in fact, it's in use in most of the major stock markets in Europe, Canada, and the United States as a backup to timing, because one of the vulnerabilities is not just the power grid and so on, but it's the stock market. So if you can manipulate a trade, if you can represent that you bought something a millisecond ago, it doesn't sound like much, but it turns out stocks are always going up and down, and there's this high-speed trading. And if you can misrepresent when you bought and sold a stock, and you did that many times over, you can crash the entire stock market. So when you think about the vulnerabilities, it's not just about you driving in your car and ending up at the wrong place. It's tied to all our national critical infrastructure.
So I'm hearing an underlying theme here of a need for resilience, right? A need for our systems not to break when GPS or some piece of the system fails. And so I'm going to turn to you, Drew, because you guys depend on your systems always working, always having coverage, 4 bars, 3 bars. You guys make money off of that. And so your system has to be resilient and has to always work. What are some of the things you do to make sure you have a resilient network?
Well, there's a lot of things we do to make sure we have a resilient network. I guess in context here, about 2 years ago, the report was delivered in December 2016. We worked with industry and government representatives. Federal Communications Commission runs a Cybersecurity Resilience Interoperability Council, and they did a study on PNT timing alternatives. And we keep talking about GPS and timing, and just to make sure you understand, from a carrier's perspective, you may have a very accurate cesium-based clock, but then the rest of the clocks we have in our network are going to be probably less accurate, and we leverage the signal from the GPS to provide if you will, it's almost like a resync timing. So it's a less expensive way to deploy it. Otherwise, you'd be spending a fortune on clocks at every single tower. So when we take a look at it, that's the way it's been deployed in all the carrier networks for quite some time. But because all of our timing is right now dependent on accuracy, is dependent on GPS refresh, if you will, the FCC got together industry and government, and we looked at different options as to how could we improve the timing and provide redundancy and resilience in timing across the entire network. And part of it is, you understand, we have a slightly different challenge in terms of vulnerabilities. Jamming tends to be localized. We're not deploying, forces in a local area to affect a change. But what we're more concerned about and what we're seeing is impacts like space weather, which sounds interesting, but is real phenomenon, and it impacts the GPS satellites because, as you noted, they're geosynchronous, they're further out than LEOs, and it impacts them tremendously in terms of radiation coming through and disrupting signals. So we have to build in resilience in our networks to actually retain the time during these types of outages, if you will, of GPS signaling because of space weather or interruptions because of that. But we also have to be able to have some kind of resilience in case the outage is prolonged. And that's what this study was based on. And it looked at 3 different types of, about 12 different options, but 3 different types of resilience. One being celestial, i.e. the use of LEOs, or the use of juicing up, if you will, the GPS signal or other types of bands that GPS could use, or other types of encoding of GPS signaling. Susceptible still to space weather. You looked at certain terrestrial type of networks, and these are developmental. And the idea is in a fiber, I can actually put in a single pulse along it, provided I'm not going through a series of routers that might create challenges in terms of perturbing the signal. But if I'm doing a direct connect in fiber, I'm going to see this signal come through. And in the third area was looking at terrestrial FM type of radios. You have companies like NextNav, Eloran out there that produce these. Bless you. Sorry. My mom taught me well. So when you take a look at these different options, the report did a great job of showing pros and cons, and it doesn't really say that this is the answer, because there is no one single answer right now. But it does provide guidance as to what the options are, and all the carriers are looking at enhancing their timing algorithms or solution sets with alternatives, and how those are going to be integrated as we move forward. So it is an awareness. Planning is happening now, and we're going to see this be deployed, if you will, in the coming years.
Super. So, Drew, you talked about alternatives. And sometimes when I think alternatives, I think backups. I think, what am I going to turn to if this main system fails? And am I ready to turn to it, right? We could have a backup to GPS today, but if I'm not ready to receive that capability, it's not going to do me any good. And as broadly as we use GPS today, there's a cost associated with switching over to this backup. So it needs to be affordable. And so, Brian, I'll start with you. The question I have, what are your thoughts on a backup to GPS? What is the federal government looking at? And what are your considerations around affordability and our ability to absorb this new technology?
It's a great question. In the department, we've been looking, there's actually backups that have already been in place for certain systems that you're willing to spend more money on. Some of our high priority nuclear missions and things like that. It's not too expensive, or it's important enough to have a backup atomic clock there on site being able to handle that. It's not something you're going to give to every soldier, out in the field. For the munitions, like I said, we have to deal with jamming, so we have inertial systems that are able to guide that through. That works for positioning, in that limited case for a short period of time. We've been looking at backups, as you pointed out. The problem usually is not buying the service, having the signal broadcast. It's putting, that receiver, in every plane, every ship, and every handheld that the soldiers have. So we're looking at ways to incorporate that. And we have this problem even with the next generation of GPS. We've improved the military signal to help address some of the jamming and the spoofing capabilities, but the expense of deploying it, slows it down, because you're going to have to take the plane in, you're going to have to go into depot, you're going to have to modify it because it's so ingrained in the system. They're not just Garmins that you stick on the windshield and off you go.
Brian, a follow-up, just to put into context, what are some of the most critical systems you worry about or that you focus on with respect to PNT resilience?
So clearly things like missile defense, some of the warning radars, use timing. You need to know, I send the signal out, how long did it take to come back? That tells you how far away the target is. Presidential communications. So in case we were ever in a situation where we're going to, hopefully never do, but going into a nuclear conference, how do we make sure that all those systems continue to work, they're not interrupted, since those are encrypted and they're often frequency hopping, so you need to keep that synced up. Those are all things that we focus on.
So I just wanted to put that into context. It's not just battlefield systems, right? Missile defense system is a system protecting us right now.
Yeah. Yes.
Right? The presidential communication system is a system the president uses all the time, every day, right? So there's a lot of aspects of national security that are very important and dependent on this.
Can I weigh in on
Please.
the economic topic? Because that's really at the heart of this. I mean, for example, we've all experienced power outages at our home, but not everybody goes out and buys a backup generator, right? The hope is somebody else figures it out and the power in your home works better. So there are clever ways of getting this whole thing kickstarted. And one of them is at the chip level, and often, in your phone and so on. Back in the day, 15 years ago, you had a custom GPS chip. And now there's a revolution going on, which is called a software-definable radio.
Right.
And so it's a chip, but it's a programmable chip, and it can do different things. It can do GPS, it can do Wi-Fi, it can do cellular, and so on. And with those chips, now you can create an ecosystem whereby changing the software, they can absorb new signals, new sources of PNT, and it's not an incredible cost to the consumer, because if you have a smartphone, it turns out the changes that are needed to make a smartphone absorb some of these new sources of PNT really don't have a cost to the consumer per se. That's one solution. The other neat idea that we leveraged at Satellus was, the world needs PNT. This is great. We didn't have $6 billion to launch a satellite system. And so, the big idea that we had is that we made an agreement with Iridium, which is the world's largest satellite operator. So they have 66 low Earth orbiting satellites that cover the globe. And to replenish a constellation like this is about $3 billion. But it turns out that we made an agreement with Iridium, and we were able to repurpose some of their assets in space without building new satellites and create this worldwide capability. And in fact, on the chip side, we were able to take what would normally cost about $20 million to develop a new chip. We took an existing chip and came up with the right agreements to reflash the firmware and created our user equipment. And I think it's going to be ideas like that kickstart this whole thing and build that resilience.
So, Greg, that's an amazing story of innovation. That's very exciting and motivating to get after the problem, to continue to find these innovative ways for affordable, resilience in PNT. So I commend you for that. It's very creative. So we're talking innovation now. We're going to segue a little bit. There is innovation going on in every sector of technology right now. You've got quantum computing, you've got quantum sensors, you've got smaller and smaller scale that we're trying to leverage atoms to do many different things. What do you guys think are some of the upcoming disruptive technologies in positioning, navigation, and timing? Go ahead and start with you, Drew.
Oh boy. So, the interesting thing was we take a look at where the network is going from the consumer perspective. You heard a lot about 5G and what does that mean? And the densification of the network that's going to happen with 5G is going to create a totally different aspect of timing. Because you're going to have in the future, as opposed to towers covering a large space, you're going to have kind of a nesting of towers where you're going to have big umbrellas covering a large area, and then you're going to have a concentration of these very, very ultra low latency towers very close to you. So you're going to see a lot of changes in the way that at least the position navigation part of it is working, and also higher demands on the timing. Method of being able to distribute the timing to these small cells, if you will, can happen within the umbrella of the larger tower. So the change is not going to be from the standpoint of the requirement for timing at the macro cell level doesn't change. We're still going to have the same challenges we have today. But when we start looking at the microcell type of it, we no longer will have as much of a dependence on this GPS constellation for the position and navigation part of it. All of it, though, still comes back down to the timing. So I can see in the near future, over the next 2 to 5 years, as these microcells are really proliferate, that we're going to have much better near-field type of communications, location-based technologies. And so it's going to change the model a lot. But all of these things still rely on that timing, and it's really more of an innovation around how you're going to distribute it down to those microcells. We still have to work through these different options of getting the timing at the macro level to be able to share it. So I think that that's going to really be what we see definitely over the next 2 to 5, even up to the next 10-year time frame.
Okay. And I hear a lot in there about intentional architecture, and we're going to come back to that one in a minute. And so we're going to segue to Brian now. Brian, I know you have a lot of insight into what the DoD research labs are doing and some cutting edge work. What do you see as some of the most disruptive PNT technologies coming?
So near term, actually, a lot of work that we've seen coming out of like the Department of Transportation would be interesting. Especially as we go to self-driving cars, it's going to be each individual car has to be able to handle the fact if it loses a signal, it can be able to adapt. But usually it's in traffic, so it can be able to get its position relative to other things which may know its position. So it can handle going into things like tunnels. So that ability to pull information from local sources that may know their position and timing and share that in a more distributed manner, I think that'll be more the near-term thing. I think what has great potential, and this is longer term, may even be decades, is some of the quantum sensing to turn basically a navigation system. You tell your phone where you are now, and then you walk 10 steps. Today it can do that. It says, okay, I know where you are now. I've sensed you're moving. But in the future, those will be so sensitive and be able to hold that for a long enough time, you could walk around all day, and then at the end of the day, it would say, because I've known how many steps you've taken in this direction and how much you've gone up and down, where are you at the end of the day? That's something the technology can't handle today. But as those quantum sensors out in the future, I think there'll be possibilities where you still have to sync it up periodically, but it'll have that accuracy to propagate that throughout time.
Super. That's exciting to me because right now our systems depend on a continuous stream of signal from satellites or some network for time. But what you're saying is that I can go periods of time, long periods of time with high precision without an external reference. I just have to sync to every once in a while.
Yes.
That's pretty exciting from a DoD perspective when you deal with subterranean or this A2AD environment scenario. But it sounds like it's a ways off, and there's good research going on.
Yeah.
Okay. Greg.
Well, what I'm excited about, I guess, my theme in revolutions is that often, one thing leads to another. And one thing that is happening, and there's a lot of money being invested in it, is better ways of delivering more globally the internet. So, everyone from Facebook to Google and so on are looking at ways to deliver internet globally. And so there's this resilience of our resurgence, I should say, in things like large satellite networks or balloons. Alphabet, Google has this project Loon to deliver these signals. So any system that does that could, in principle, be adapted to also deliver position, navigation, and time. So if you know where the source is, and it has time, if it has a clock, and the beauty of this is that the speed of light is the speed of light. So the delay that between you receiving the signal and the time that it was sent defines a distance, really. And that is the magic of how GPS works. But I think it could be expanded to all these new things that are happening for internet applications. I think will ultimately be PNT applications. And my company is trying to do that now with Iridium. Iridium was originally a communication system. It still is. It's the largest satellite communication systems in the world. And we've found this way to turn it into a PNT system. And I think that more broadly, that's going to happen with other technologies that are going out around the world for the internet.
So underlying all this, and something you mentioned, Drew, that I'm going to pull a word out of, architecture. It matters, it sounds like, to have very intentional architectures. And I know from experience, you want an architecture that is resilient so that you can apply upgrades, and it's got different capabilities where it doesn't have single points of failure, et cetera. I know T-Mobile, you guys are really focused on looking at your entire system and architecting it well. I heard that in your comments. Greg, I heard your comment about applying multiple architectures and looking at the Project Loon and others and their architecture and leveraging that. And Brian, I commiserate with you from my time in DoD, where in DoD, we haven't done a good job at architectures in the past. We kind of build an airplane, we build a tank, we build a piece of equipment for a soldier, or even we build a radio and a satellite separately that have to work together. And then we say, all of you guys go work together and have resilience. And I know there's efforts in DoD to address architectures on many layers, including P&T. But I just wanted to pull that out and acknowledge that architecture is key. We've got about 10 minutes left, and what I'd like to do is open to the floor for questions for this esteemed panel. Any questions? We've got one in the back.
Are you worried about privacy?
So the question was, are you worried about privacy? And I'm going to extrapolate on that. Privacy with respect to P&T. It could be data privacy. It could be individual privacy. So we'll let everyone have a shot at that one.
We talked about this some last night when we got together about location tracking, location aggregation. Obviously, as a wireless carrier supporting consumers, we're extremely concerned about privacy and take a lot of measures to protect the privacy of our consumers. When you take a look at what happens with location technology and you combine it with the amount of information that's out there in social media and the aggregation of location data, tracking materials, information like that, it does become really challenging, and you have to maintain separation of this information. You also have to protect and not disclose it. And this is an ongoing requirement that we have to be aware of and to take the proper measures to protect it. We work with other carriers, we work with government to ensure that we have the proper procedures in place to protect it. And when something goes wrong, we move quickly to rectify it, because that's not privacy is something you can't compromise. It's something you have to really take to heart. And being the young carrier, we do that.
All right. Okay.
So let me take just a little different spin. I mean, being the Department of Defense, privacy maybe isn't the word we use, but counterintelligence.
Right.
And the ability of our enemies to pull data out. So we've already seen, people with Fitbits, and what are the routes they walk, where are they being stationed. More and more stuff is being, geotagged, and there's big data that's able to pull all that information forward, So over years they could say, oh, you're a person that works these kinds of sites, this must be your career path. Oh, you went to this site. Wait, I don't have that flagged as one of those kinds of, things. So there's tons of information. It's going to become even bigger as they pull together, that geotagging of data and are able to look at that from a holistic sense. So we're definitely concerned about what you can do there.
Okay, thanks, Brian. Greg?
Yeah, well, a two-part answer. The first thing is we've all seen the James Bond movies where somehow, to somehow get to the heroic ending, somehow GPS was manipulated and so on. And it's worth all of you knowing that GPS is a broadcast system, which is to say that if you purely have a GPS receiver or a Satellus receiver, there's no communication back to the system that tells you where you are. You know where you are, but Big Brother, strictly speaking, doesn't know where you are. In the Fitbit example, what happened is it was the communication aspect of it that was the leak, if you will. So if you know where you are and you tell everybody, then there's a problem. But in its purest sense, usually these devices figure out where you are. But it does, the question I think more broadly could be applied to cybersecurity and security in general. And that is something that we take very seriously at Satellus. And I'm going to turn into a geek here for a second. I can't help myself. But
Go ahead, Greg.
so
we prepped them for it already.
all right. So it turns out that GPS is like think of a light bulb in space, a GPS satellite, and it lights up about 1/3 of the Earth. So that signal comes down and it lights up about 1/3 of the Earth. And for the sake of argument, the signal that's received in Florida is exactly the same radiation that you might get in North Dakota. So someone that's skilled in the art and has $100 worth of equipment can take the signal in Florida and make it seem that they're in North Dakota. So we want to do things like credit card transactions, right? You want to prove where you are, because proving where you are is part of proving who you are, right? So we have identities, and we don't want our accounts stolen or anything else. So proving where you are is a neat idea, and to make that an idea that really works, it has to be difficult for you to misrepresent where you are.
Right.
And in the Satellus case, what we've done is instead of just lighting up 1/3 of the Earth with one signal, we actually have 3,000 different beams that light up the Earth. And these beams turn on and off constantly, and each one has a changing cryptographic key. And so it looks like a kaleidoscope, if you see this. And here we are in this one place, and just in this region, there's a unique set of keys that we're delivering here that are not the same as the ones over there. And so we're very interested in getting into the idea of proving who you are, authentication, by proving where you are. And so, for example, let's say one of the things that I think is very valuable is the human genome. And I think in 10 years, you're going to want to tell your doctor something about your DNA so that they can cure you of whatever malady that you have. But you don't want a bad guy to get that, because they could hurt you, right? And so if you could take that information and you could encrypt it, and you could say this information can only be opened at a certain time at a certain place, and the recipient has to prove that I'm at the Mayo Clinic and I'm the authenticated desired recipient, I can open this document at the right time in the right place. But if, for example, the North Koreans steal that same document, they can't open the document because the authentication keys from space, in this case, wouldn't enable them to.
Right.
And we're very excited about that application.
That's a great answer. Yes.
Can I add one?
Go ahead.
It's interesting, because we were talking about this last night as well, is that as we look at the early days of location within the wireless industry, triangulation was used. And in that case, what happens, as opposed to the device knowing where it is, the network knows where you are. And these are contrasting opportunities for positioning technology. As we go to 5G, of course, we're going to get smaller and smaller microcells that are going to know much more precisely where you are. And the advantage of that becomes an alternative. I can have my iPhone and I can put a little piece of software on it, and it can take whatever GPS signal you get and actually fudge it and report back something different to an application within the network. So that's known. It's something that can be done. But you can't fool the network, because the network has you registered in it. So it's interesting how we're going to have all these different types of capabilities, and it depends on the application, what you're trying to address, and how you're trying to solve it, is whether network-based or device-based or some of these newer near-field communications-based types of applications are going to make sense, especially when we're talking about indoor location, which is one of the challenges for public safety. And we're working with a lot of different capabilities within the cellular network about using near-field communications, Bluetooth, Wi-Fi as alternatives to the regular GPS or triangulation to enable public safety to know what building, what floor, dispatchable addresses, things of that nature. So these are all technologies the wireless industry is working on that are a little bit different than the P&T discussion we're having today, but they are related.
Great. Great answers. It sounds like we could have a panel on this topic of privacy and security alone. Okay, I think I've got time for one more question. Any questions?
Sure, down front.
If you're looking forward to managing something like a fleet of autonomous vehicles or highway traffic, how great of a challenge do you think the data volume will present to these networks?
The data volume to the networks. I guess I'll start off. When we talk about, let's take it up one step and say IoT, the Internet of Things. When you look at 5G, you have three different types of networks. You have either, or services. You have these ultra-low latency type of services, which mean the information has to flow back and forth very quickly. Millimeter wave helps to address that. It also has a much greater bandwidth, but it's really about speed and latency there. And that's probably what we're going to see more when we talk about autonomous vehicles, that type of response. The neat thing about that is if I drop packets, it's probably irrelevant because I'm getting so many different pieces of information. But then you can start layering on the cake. So you have this really, high frequency, high bandwidth, ultra low latency. Then in the middle section, you have stuff that penetrates buildings, this mid-band spectrum. And that actually gives you a lot more penetration. That's for more of the communications we're used to today, but it still has enough bandwidth that we can actually deliver high bandwidth video, things of that nature. And then finally, at the top part, you have this low frequency, sub-gigahertz. That really penetrates buildings well. It also goes longer distance. And as you layer these three different types of networks and spectrum, that actually enables what 5G is going to be able to do, from the ultra-low latency to also being the high bandwidth, high pipe, or large pipe type of services, as well as ultra-reliable. So what ends up happening is you're going to have all these different services that are going to take the advantage of whichever spectrum is most appropriate for that specific service, and you're going to integrate it across so it's always available for the different services. And it becomes a little bit of a take a piece of this, a piece of that, and put it together for what you need. Does that help you? Make sense?
Okay. Anything else?
Well, it's an interesting question because, when you're managing something like driverless cars and so on, there's different elements to it. But people think about this a lot in this day and age, and I guess it's worth noting that the 4 billion GPS devices today, the reason that the satellites aren't overloaded is because the satellites transmit a signal that we all can use. And it turns out that there's really, beyond how many billion GPS devices we can fit on the Earth, they can all leverage that signal. The same applies with satellite time and location, my service. So in that sense, the positioning part of this won't be overloaded. The trick is merging that positioning, timing information with the other communication and data that Drew just spoke of. I mean, that's really the trick. And with regard to autonomous vehicles, just like Brian said, what will happen is there will be sort of fail-safe modes where when there is a data outage, the car will be more autonomous, and it will have fail-safe systems to ensure that it doesn't hit the car in front of it. But of course, it'll be a lot cooler, and there'll be much more features for the user when all the data is flowing. So it's fascinating how PNT interconnects with this whole data service, and it's kind of hard to pull one thread and separate it from the other. But in that sense, the PNT systems won't be overwhelmed, but we have to keep our eye on the data systems.
Right. All right, so on that, I think we're going to conclude our panel. And in closing, I really hope this communicated to everyone the criticality and the depth of technology in position, nav, and timing, and how important it is to our modern society. And I want to thank you for your attendance, and I want to thank the panel members for such a wonderful panel. Thank you.